We're going to finish talking about rates of reactions. We first talked about the collision theory and that in order for a reaction to take place, the molecules must collide. They have to collide with the right amount of energy, and we call that activation energy. And then they had to collide with the correct orientation. So today we're going to talk about how we actually calculate the rate of the reaction and how we can affect that rate. So either speed it up or slow it down. So it's really important that we can monitor for a lot of different chemical reactions how fast they occur. So to calculate the rate of a reaction, we're going to use this equation here. So the average rate is going to be our change in concentration divided by our change in time. So remember, in chemistry we measure concentration in molarity, or capital M. So if you notice in the table over here, we have values of concentration, we have values of time, and then we have the rate that was calculated. Now a couple notes on the equation. So whenever we see this triangle, that's the Greek letter delta. And delta in science, or the triangle in science, means a change in. And it's always going to be the final minus the initial. And then also the brackets. So here normally we wouldn't see the word concentration, we would see a name of a substance, like either H2O or C4H9Cl in those brackets. And so brackets mean concentration. So triangle, change in, brackets, concentration. So a change in concentration. And then the T in this equation is representing time. Most of the time we're going to see time in seconds, but sometimes it could be minutes. So the change in concentration divided by the change in time. So again, it's always final minus initial. So the top would be the final concentration minus the initial. Final time minus the initial time. A lot of times that initial time is 0 though. So for example, if we wanted to calculate the 1.9 times 10 to the negative 4th, the rate, we would have taken 0.0905 minus 0.1, so the final minus the initial, divided by the change in time. So it would be 50 minus 0. So let's try an example using this equation. Change in concentration over change in time gives us the rate, how fast it's going to react. So here we have a problem. If the concentration of nitrous oxide is 0 molar at time 0 and 0.01 molar 2 seconds after the reaction begins, what is the rate of the reaction? So to calculate this, we're going to use our equation. So that our change in concentration over the change in time. So we're going to take our final concentration. So after 2 seconds, we're at 0.01. So 0.01 minus our initial. So initially we had 0 molar, 0.00 in brackets, divided by our change in time. So our final time was 2 seconds. Our initial time was 0. So to simplify, we would take 0.01 minus 0, is that, divided by 2. So we should get an answer of 0.005. And now the unit for rate is just what we used to calculate. So 0.01 was measured in molar, 2 was seconds. So our unit is going to be M, molarity per second, M/S. So our change in concentration divided by our change in time. Let's try another example. So the reaction data for the reaction between butyl chloride and water is given in our table. We want to calculate the average rate over this time period expressed as moles of butyl chloride consumed per liter per second. So our same equation, our final concentration minus our initial concentration. So we have some time here at time 0, we have a concentration of 0.22. At time 4, we have a concentration of 0.1. So again, we're going to take our final minus our initial. So to get the rate, we're going to take our final concentration, 0.1, minus our initial, so at time 0, 0.22, divided by the change in time. So we went from 0 to 4 seconds. So final 4 minus initial 0. So let's simplify. So we're going to take 0.1 minus 0.22. We get negative 0.12. Divided by 4 minus 0 is just 4. So we're going divide the two then. I'm going to get an answer of negative 0.03. Now to get our units, remember our top numbers were molar, our bottom numbers were second. So our unit is going to be molars per second. So a really simple equation, all you have to do is find your final and your initial, subtract the two, and divide them. Now you notice this one has a negative value. If we go back and look at the reaction that's taking place, which is this one, butyl chloride, we're losing it. It gets getting converted into our two products. So your rates can be negative, and it will be negative if it's a reactant. So butyl chloride was a reactant, so we're losing it, so our rate should be negative. In this other example, we were talking about nitrous oxide here. And so it's a product, and we're making it. So our answer on that example was a positive number. Okay, let's talk then about how we can speed up or change a reaction. So the first way is by changing the physical state of the reactants. So a reaction will happen faster if the mixture is more homogeneous. Remember, homogeneous is you can't see the different parts. It's all mixed together very well. So if our reactants are really mixed together, so they're not separated, our reaction should occur faster because the molecules will be closer together. They'll be able to collide. So the more homogeneous your mixture is, the faster the reactants will occur. The reaction will occur. Okay, another way we can change the rate of the reaction is by changing the concentration. So remember, concentration just tells us how much of our reactants are present. Remember, reactants are things we start with. And so as we increase our concentration, you can kind of see this. The picture on the left here, we have very few molecules. On the right, we have a higher concentration because we have more molecules. So the higher that concentration is, the faster the reaction is going to take place. And that's because there's a greater chance of collisions. Here on the left, there's not a lot of molecules. So their chances of hitting one another is smaller than the chances on the other side. Think about our freshman example. If we were to throw two freshmen in the gym and blindfold them and tell them to run, okay, their chances of hitting one another are very small. But if we put the whole freshman class in the gym and told them to run around blindfolded, okay, their chances of collisions are a lot greater. And remember, in order to react, they must collide. So the more chances you have for a collision, the faster the reaction should go. So the third way we can change the rate of a reaction is by temperature. So the higher the temperature is, the more kinetic energy a molecule is going to have. So what is kinetic energy? Kinetic energy is energy related to the motion of the particles. So the faster they're moving around, the more kinetic energy they have, the greater chance of colliding. So at higher temperatures, the molecules are moving around a lot faster. So think about our freshman example again. If the freshmen are sprinting around, they have a high temperature, okay, their chances of collisions are going to be greater. If our freshmen are only gradually walking around, their chances of collisions are a lot smaller, so they would have a lower temperature. Same thing happens with our molecules. The higher the temperature, the more movement they're going to have, the more kinetic energy they have. So if they're moving around more, they're going to collide more often. So that affects our first statement of our collision theory. So the more collisions, the faster the reaction. It also changes our second part of our collision theory, that they have enough energy when they collide. So if they're moving around faster, when they collide with one another, they're going to have a larger amount of activation energy. So the greater the chance that collision is going to be successful in making a product. So they collide both more often and with a greater amount of energy. The next thing, we didn't experiment with this one in lab, but catalysts are going to speed up a reaction as well. If you remember our elephant toothpaste example, when I put in the hydrogen peroxide with the soap and just let it sit there, nothing really happened. It would have taken years for that hydrogen peroxide to break down. But when we added the potassium iodide, the catalyst, all of a sudden it foamed up and shot out of the graduated cylinder. And so that catalyst sped up that reaction. So what a catalyst does is it speeds up a reaction by lowering the amount of energy needed. So when the particles collide, they don't need as much energy. So the collision can be more successful at a lower temperature. So catalysts speed up a reaction by lowering that activation energy. So catalyst effect, part 2 of our collision theory. One thing about catalysts is they don't actually get used up in a chemical reaction. We add them to the reaction, they speed it up, they lower that activation energy, but they are still there at the end of the reaction, even though we've made products. So catalysts are not consumed during the course of the reaction. So for example, this is palladium. It's a rare metal and it's very expensive, more expensive than platinum, like platinum rings and stuff like that. So palladium, very expensive. And it's used as a really good catalyst. But we can use the same piece over and over again in the reaction because catalysts don't get consumed in the reaction. They're still there. And so we don't have to waste any of it, even though it's an expensive metal. So we can just use it over and over again for our different reactions. So here's a little catalyst of some various cattle. Okay, the last way we can affect the rate of our reaction is by changing the surface area. So when more surface area is exposed, the reaction will occur faster. So a good kind of analogy to this one is trying to dissolve sugar. If you take a big block of sugar and put it into your tea, it takes a long time for it to dissolve. But if you were to crush up that cube into little small granules and add it to your tea, it's going to dissolve a lot faster. So the same thing here. The larger your surface area is, the faster the reaction is going to occur. And that is because there is more area for a collision to occur. So if we have this piece of metal and we flatten it out into a big long sheet, there's more area for the other particles to collide with it. The smaller the surface area is, the harder it is for it to collide because there's not as much exposed to the other particles. So if you remember our steel wool example when we burned it, I pulled apart the steel wool, so I increased its surface area, so more of it was in contact with oxygen. If we were just to leave it in a clump like this picture, it'd be very hard for all of that steel wool to burn because not all of it's getting exposed to the oxygen. So if we were to increase that surface area, the reaction should occur faster. So let's check your understanding. So I'm going to read the question and the answer, pause it, see if you can determine which one is correct. So our first learning check. Why does a higher temperature cause a reaction to go faster? Is it A, only because there are more molecules per second? B, because more collisions occur with greater energy? Or is it C, there are more frequent collisions and they are of greater energy? So the answer should be C. There are both more frequent collisions, so collisions occur more, and the collisions are more successful because they have a greater amount of energy. So it should be C, both 1 and 2 of our collision theory. Okay, question 2. Why does a higher reactant concentration make a reaction faster? Is it A, only because there are more collisions per second? B, only because collisions occur with greater energy? Or C, there are more frequent collisions and they are of greater energy? So the answer should be A, only because there are more frequent collisions per second. So changing the concentration only changes part 1 of our collision theory. More reactants must collide. And so the more you have there, the more there are going to be more collisions. Okay, number 3. Why does a greater surface area cause a reaction to proceed faster? Is it A, because there are more collisions per second? B, because collisions occur with greater energy? Or C, there are more frequent collisions and they are of greater energy? Okay, so this one should also be A. So the greater your surface area is, the more collisions that can occur. And our last question, what happens to a catalyst in a reaction? Is it A, it is unchanged, B, it is incorporated into the products, C, it is incorporated into the reactants, or D, it evaporates away? So the answer should be A, it is unchanged. So catalyst speeds up the reaction by lowering the energy, but it does not get consumed in the reaction. It's still there at the end.